Hello friends, welcome to this new lecture on amortized analysis. In this lecture, we are going to focus on how to work with amortized analysis for any algorithm using the potential method. In the last two video lectures, you have seen how we handled amortized analysis using the aggregate method and using the accounting method. In this lecture, we are only going to focus on the potential method. So let's get started. So as we all know, that an amortized analysis is done in cases wherein we have a certain portion of an algorithm which is very expensive and it makes the algorithm slow. So in this case, we see that this particular part is slow. So can we distribute the complexity of this particular expensive operation over all the rest of the operations which are not that expensive? So we try to distribute it over all the other operations to make that particular operation look normal. Right, so this is how we can say that the cost per operation is much lesser than the total cost. So in this video, we are going to focus on the potential method and we are going to take three examples for it. First is the dynamic tables, next is the stack operation, and third is the binary counter. Now, so first let's understand what is an accounting method. In the accounting method, okay, we are working with respect to the potential energy, or we could say a potential at a particular state in the algorithm. Okay, so we are going to check out what would be the state at a particular what would be the potential energy at a particular instance. So in this case we can see that we have an amortized cost AI at a particular operation which is equivalent to the actual cost, that is CI plus, and we see that we added with the potential difference, okay, from the last stage till the new stage, that means the current stage. So we add up the potential difference in this case. Now, so we can say that the total amortized cost, okay, or the summation of all the amortized cost for over all the operations would be summation of CI, that is the actual cost over all the operations, plus the difference between these stages or the different instances. So we are now we also see that it could be converted into directly phi I minus phi I minus 1 could be converted into phi n minus phi 0. Okay, so we'll come to that also. Let's understand with a deeper understanding how this works. Now, so we see that CI dash, okay, in the last slide we saw that it is AI, that is your amortized cost. We can also represent it by CI dash is equivalent to CI plus the potential difference. Now, in this case, why do we add the potential difference? Because we want our amortized cost always to be greater than the actual cost. Why do we need it? So that later we could use this stored up energy, okay, in the times when it's required. Okay, so let's proceed. So what is amortized cost? Amortized cost actually bounds the true cost. So how does it bounce the true cost? That means it uses something to add up to the actual cost, right? Now, so we see that we add up the potential difference between two stages. So that is the current stage minus the last stage. Now, we can also directly represent that for all n operations by directly making it phi d minus phi d0. And this is done by using the telescopic series. Okay, now in this case, as we see that it is a particular positive number, okay, we see that dn is greater than or equal to 0, and at the initial state there's no potential energy, okay, so there's no potential at the first stage, so obviously this is going to be a positive number. If the actual cost is added to a positive number, that means that the amortized cost is greater than the actual cost, so we can clearly write it as amortized cost is greater than or equal to the actual cost. Now, so let's understand with the help of a dynamic table. Now we all know what is a dynamic table. You can refer my previous lectures and I'll put up the links of the previous lecture in the description of this video. So you can go over there and you can check out how we work out in dynamic tables. So now let's understand with the help of an example. But in this example, we see that we make something phi. Okay, this is a phi function which is going to help us create some extra energy needed for further operations. So in here we can see that like in the accounting method, we had this bank variable. But do we anywhere see bank mentioned in this potential method? No, we don't have it. So there's a function which is actually replacing this bank and is going to take care of how this particular extra energy could be stored and used up later. So let this function be for now be phi is equal to 2 into number of items in the array minus the capacity of the array. So this function is going to help us with the extra energy. Now, so let's get started. So in the previous video also you might have seen this particular table, and we see that as item 1 comes, okay, how does the dynamic tables behave? So we have a size for that, that is 1. So the cost of operation is just 1 because we need not do anything, we just need to insert. So the total cost is 1. But for the second element, we need to double the table size. We need to copy the old element, which is one element, and then we have to add the second element, which is the second value, which is having value 2. So obviously cost of operation insertion is just 1, but copying the old element is also costing us 1, which is taking the total cost to 2. Right. So similarly for the third element, obviously we'll have to double the table size from 2 to 4. So you can see the previous 2 needs to be copied. So the cost of copying and doubling is 2, and insertion is 1. So that makes 3. Okay. For the fourth element to be inserted, the table size is already 4. Nothing to be done. Only the cost of insertion is applied. That is cost of 1. So the total cost is 1. Now, for the fifth element, we can see that we need to increment the table size. That means the double the table size. That means I have to copy the first 4 elements inside the new array, and I have to insert the fifth element. So the insertion cost is 1, but the doubling cost is 4 because we got to copy the previous 4 elements. So the total cost taken is 5. Similarly, you can see for the sixth element that the cost of operation is just 1 because there is some space available in the table, right? Because we have table size of 8. And similarly, as it is just 1, so the total cost is 1. Similarly, for the seventh element, the cost of operation is 1, so the total cost is 1. For the eighth element as well, the cost of insertion is just 1, so the total cost is 1. For the ninth element, you see that there's no space left in the table, so we need to double the table size, and we need to copy the first 8 elements inside the new table. So that means the cost of copying is going to be 8 plus insertion of the ninth element, that is 1. So 1 plus 8 is equivalent to 9. So that is how we work. Now let's understand how phi helps us. So phi is what? It is 2 multiplied by number of elements inside the array minus the size of the array. So you can see it is 2 multiplied by, this is first element, right? So 2 into 1 minus 1, so that is 1. Right. Similarly, calculate phi for the next row that you can see. So it is 2 elements inside the array. So it is 2 multiplied by 2, and the table size is also 2. So phi is just 2. Similarly, for the third element, you see that we have 3 elements inside the array, but the array size is 4. Right. So we can clearly say that it is 2 into 3, that is number of elements, minus the array size. So that brings up to 2. For the fourth element, you see we again multiply by 2 into 4, and the table size is also 4. So it is just the remainder is 4. Okay. Similarly, for the fifth element, you see that it is 2 into 5 elements inside the array minus the array size is 8. So that brings up to 2. So now you can see the phi is always a positive number, right? And this is going to help us to account, okay, to something bigger, okay, to have a particular balance that can be used later. But we don't have a balance variable here. We are just going to use this function directly to find out the amortized cost for a particular instance, or for a particular row, we can say, looking at this table. So you can see what is my amortized cost. Amortized cost is the actual cost plus it is the potential, or it is the phi of the previous stage minus current stage minus the previous stage. So you can see the actual cost needed, CI. What is CI? Actual cost needed is just 1, right? So the actual cost needed is just 1 plus what is the phi of the stage, that is 1, and obviously of the previous stage when we started there would have been no phi because there would have been no element inside the array, right? So it is 1 minus 0, so we can directly write 1 plus 1 minus 0 is equivalent to 2. Similarly, for the next step, you can see this is the actual cost, that is the total cost, CI 2 plus I am subtracting the current phi minus the previous phi. So current phi is 2, the previous phi is 1. So you can see it is 2 minus 1, so it brings me the value 3. For the third step, again, you see that the total cost is 3 plus the current state minus the previous state, okay, and that brings about the value 3. In the next step, you can see it is 1 plus the current state is 4 minus the previous state, that is 2, and this brings about the value 3. Similarly, next stage you can see we need like the total cost is 5 plus so 5 plus we have the current state, that is 2 minus 4, right? So that is going to give us minus 2. So 5 minus 2 is going to be 3. So this is how we proceed. So you'll see that in the good examples later. So like in the last stage, okay, we see that the total cost is required is 17 plus It is the current state where that is 2 minus the previous state that is 16. So that is again bringing about the value 3. So can you see now the amortized cost is almost 3 for all the operation. Haven't we seen this in the accounting method? Wasn't it the same? Yes, it is the same. But in the accounting method, you had a bank variable. But here we don't have the bank variable. We have this function which is helping us get the same value. So we can say that amortized cost is similar for both the cases if we take for accounting method or for potential method. So the working is kind of very similar, right? So let's understand this with the help of other examples as well. Okay, and you can clearly see that because we're having a good amortized cost, okay, all the expensive operations have been taken care of. So we are where you can see the total cost would have been 9, but as the amortized cost was getting charged extra, that was 3 in every operation. Okay, this 9 has been compensated, and so we never have to charge a high amount at any particular point of time, and it will be taken care of by the amortized analysis. Okay, now the question is, will this be the only function? No, you can define your own function, but you have to see to it that whatever function you define has to be the tight upper bound, and it couldn't be some any extra amount. Okay, otherwise all the operations will look like an expensive operation. So see to it that you don't charge too much for every operation, but just what is needed for the expensive operations to be taken care of later. Right. So let's proceed. Now, so the next example is of a stack. Now we all know what a stack. There's a push operation, there's a pop operation, right? So the push operation takes in more amount of energy, uh, and pop takes less. Okay, this we have seen in the accounting method as well, wherein we said that let's charge 2 for the push operation and 0 for the pop operation. Okay, so let's proceed and see in the stack example. We have been through this a particular slide in the previous videos as well. We clearly see that the push operation is a constant type operation, even pop is a constant type operation, wherein multi-pop, we clearly know that it is minimum of k comma s, wherein it depends on, suppose if we are saying that we have 60 elements inside the array and we want to pop of 40, so the complexity will be only 40. So it is the value k. Okay, wherein another way around, if suppose I'm asking 60 to be removed, but I'm having only 40 elements inside the array, then I can't remove more than 40 elements because that's not possible. So obviously that will be the mod of S. That is the amount of elements currently inside the array or inside the stack, you could say. So let's proceed and understand how we'll be working with the stack example. So we all know this that we are going to find out again the potential function, right? The potential value. So that is phi of d0. Okay, and similarly, and finally, we are going to help it out for the stack example. So let dk denote the data structure after the kth operation. So what is this dk? Dk in this case is our stack, okay, or we could say it's an array which is holding the elements. So this the array is going to give us what is the potential. So let's say let's talk about a bank balance. Okay, so suppose in my account I have some amount, so that amount stands out to be the potential at that point of time. Okay, so in the next stage, possibly suppose I have donated some amount or I've used up some amount. Okay, so the potential of my balance, oh sorry, account is going to get decreased, right? So potential is how much do you hold in that particular time. So in this case, it is like how much do you hold in the data structure at a particular point of time. So this is a stack example. When we say that let the number of items inside the stack be the potential function, that means the current capacity of the stack, also sorry, the number of elements inside the stack is the potential function. So at the start, when there is no element, obviously phi of d is going to be 0. So at the stage d0, the potential energy or the potential function is going to return me a 0 value because there are no items. Obviously, for all the further operations, there's going to be some items in the stack. So it is always going to be greater than or equal to 0. That's what written over here. Phi of dy is greater than or equal to 0. Now, let's start calculating the potential function for the push operation. Now, for the push operation, we see that we have the basic cost, that is Ci, that should be charged 1, and we obviously put up some particular extra potential energy, right? Now what is that potential energy? Is the difference between the current state minus the previous state. So potential energy at the current state, suppose I'm talking about a stack which is having 15 elements. So the current potential energy would like previously it would be 15, but after the push operation it would be 16, right? So finally the potential difference is going to be 1 between the two states, right? So you can clearly see that 16 minus 15 is going to be 1. Now, how did we get it? So we see that in the push operation, when we push an element, the size of the stack is going to increase by 1, right? So the current potential is going to be 1 more than the previous state. So the current potential is stack size plus 1 minus the previous potential, that is stack size. So obviously the potential is going to be coming out as 1. So how do we work it out in the push operation? Is the amortized cost is CI, that is the current cost, plus the potential difference, and the potential difference came out to be 1, and obviously the push operation is going to take a cost of 1, so we have 1 plus 1, which is equivalent to 2. Now, would it be different for the pop operation? Yes, obviously in the pop operation there will be a slight difference, like the current state will be one less than the previous state, right? So the previous state will be having one element extra. In the current state, I'll be having one element less. So if this is the case for the pop operation, you'll say that it is stack size minus stack size plus 1, because the previous state would be 1 more. So this output would be what? Minus 1. So if it is minus 1, right? So the current cost minus the previous cost, right? Sorry, current cost plus the potential difference, which is minus 1. So it will be 1 minus 1, which will be equivalent to 0. So there will be no cost charged in the case of pop operation, right? So we can see that over here, that for the push operation we charge 1 extra, so it is coming out to be 2. For the pop operation we don't have to charge anything, right? So here the ck dash is what? It's the amortized cost, okay, and ck is the current cost. Now for the multi-pop operation, you can see that let's take an example. I'm having 10 in my array or in my stack. So obviously if I'm taking out 5 elements, the potential difference is going to change by 5. So 10 minus the current state would be 5, the previous state would be 10, so it is 5 minus 10, which is minus 5. So you can see the actual cost needed for popping also is 1, that is 5, minus the potential difference, that is also 5. So you can directly know that the output is going to be 0. Now this example of stack example is almost equivalent to like purchasing a ticket. Now, when you purchase a ticket to go from station A to station B, you could just buy a ticket of one side, go to station B, then while coming back purchase another ticket from B to A. But in the case of potential method, you can clearly see that we can directly proceed by purchasing the ticket of both the sides. That means a return ticket. So if you purchase a ticket for both the sides, you don't have to wait at station B for a ticket while coming back, while returning. You can just come, right? So it's that for both operation, you're just paying once, right? For push, you're paying double so that you don't have to pay for pop. Similarly, for multi-pop, just think that your family is going on a trip, right? So if a family is going on a trip, you have to pay again just once for the return ticket, and when they come back, they don't have to pay anything. So that is the multi-pop operation. So I hope you have understood the stack example. Let's proceed with another example, that is the binary counter. So you can see in the binary counter how things work. So you can like go to my previous videos and check the functioning of the binary counter. We'll just take it in a brief in this example. So you clearly see that at every stage we increment the counter. So how does it work is that let's take the first row as one array, and this array has been passed as an input. So you see all the values are zeros for this array. The position 0 of the array is also 0, position 1 of the array is 0, position 2 is 0, and position 3 is 0. When this goes as an input, what happens? So we see with the eyes pointing to 0, that is the first position of the array. We check whether it is less than k, that is the size of the array. Yes, it is less. But we also check whether the first element, the position I, is it equal to 1? It is not. It is 0 right now. So obviously I can't go inside the while loop. I directly check the if statement next. And the if we see I is less than k, that is 0 is less than 4. So we directly convert that particular element into 1. And the increment is done. And you get the second row as the output of the first row, which was the input. So you can see this 0 got converted into 1 because of this if statement. Similarly, in the next part, we'll pass the second row as the input, and we should be getting the third row as the output. So let's check what happens. So you can clearly see as 1 is there as the first element. Okay, this while condition completely gets satisfied. A of I is turned into 0. So you can see 1 is turned into 0. We increment I, that means we are pointing to the first position now. And obviously first position is having 0, so while loop won't work anymore. We have to come out, and obviously after we come out, we change wherever the I is pointing right now to 1. So this particular 0 is getting converted into 1. So this is the output. Similarly, when third goes as the input, we see that the first element directly is 0, so the while won't work. We directly convert it into 1. Okay, so you can see the fourth, it's just a minor change that 0 got converted to 1. But when fourth goes as the input, you can see the while loop works for 2 rounds. That is for a of 0, wherein a of 0 is 1. So I convert it into 0. I go to the next position. I again check the next position is also 1. I convert it into 0. But next position is 0. So I have to come out of the while. When I come out of the while, wherever my current I is pointing to, I make it into 1. So you can see 0 is converted into 1. So the fifth is the output of the fourth row. That's how binary counter works. Now let's see how this works with the help of potential method. So we have seen that the basic operation, in every single operation, there's a flip from 1 to 0 and there's flip from 0 to 1. But we know that 0 to 1 is very frequent. It is happening in at least once. Okay, it's happening once in every single operation. That is every single state change from row 1 to 0 to row 2 to row 3, right? So we can say that for in the accounting method, we had charged extra for the flip from 0 to 1, so that we don't have to charge for the expensive operation, that is flip from 1 to 0, because flip from 1 to 0 can bring about an expensive charge. Sometimes we had seen in the previous video. Now, so how could we work it out? So in this case, we can say for a binary counter example, we can define the potential phi I after the ith increment to be the number of bits with the value 1. That means here we can say that we have no potential, because in this particular state we have no ones. But in the next row, we can see that we have one value as 1. So we can say the potential of this particular stage is 1. In the next, will again have to say that there's only single one, the potential is just 1. But in the fourth row, we can say that the potential is 2. Similarly, in the last stage, the row number 16, you can see that we have all 4 ones, and we can then clearly say that the potential for the 16th row is 4. Right. So how do we work it out? So we have the current CI. CI is what? We charge for both the flips from 0 to 1s and 1s to 0s. So we just need to add them both, right? And what is the phi difference? Okay, that's the potential difference. So it's the potential difference of the number of ones that was there in the previous state, right? That we subtracted by the number of ones which is there in the current state. So it is the number of ones in the current state minus the ones in the previous state. So that we can obviously get it by checking the number of bits that change from 0 to 1 in the current state minus the number of bits that change from 1 to 0, right, in the current state. So that's how we can manage it. So if we want to do it that way, we can just add up CI plus the potential difference, because that gives us the amortized cost AI. When we do that, we can see that this right hand side will get deleted because it is plus and minus, ones to zeros. This goes away. So it is 2 times the bits change from 0 to 1. So it is 2 times the bits change from 0 to 1. So isn't it same like the accounting method? In the accounting method also, we had seen that we charge twice for the operation of 0 to 1 to compensate for the expensive cost of 1 to 0, right? So let's see how it works in binary counter now with the help of this table. So you can see the phi value is the number of ones, right? So in the initial state it is 0, in the next state it is 1, in the third row again we have only one value, so it is 1. In the fourth we have 2 ones, this is 2. In the fifth state it is just 1, so it is 1. In the sixth state we have 2 ones, that is 2. Okay, similarly in the last state you can see it is 4, that is phi value. Now what is CI? CI is the number of bit flips. So it could be anything, 0 to 1, 1 to 0. So in the first stage, you can see it is 0 to 1, so only one bit change, so we say 1. In the third row, you can see at position 0, there's a flip, and at position 1, there's a flip. So that's why there are 2 flips, so the cost is 2. Similarly, you can go ahead and check, like suppose from row 11 to row 12, you can see in the position 0, there's 1 flip. In the position 2, so no, I don't think so. From 11 to 12, when I'm going, I can only see 1 flip, right? Rest 3 are same. So yes, let's check the cost. Yeah, it is just 1. So it is just 1 flip. Now let's go with the amortized cost. How does it work? It is the current cost plus the potential difference of 2 states, right? So at the start we can see there's no cost because there's no change, and the potential state is also 0 for both the stages, right, for the current state and the previous state. So now for the next stage we see that the total cost is 1 that is needed. The potential is also 1 minus the potential of the previous state, which is 0. So it is 1 minus 0. So the final potential comes out to be 2. In the next state, we see the cost is 2 plus the current potential is 1. The previous potential is also 1. So if we subtract that, we get 0. So the final amortized cost comes out to be 2. In the next state, we see that the cost is 1 the current amortized, sorry, the potential is 2, the previous potential is 1. So 2 minus 1 gives me 1. So final value comes out to be 2. You can go ahead and check it anyway. That in this case, the current cost is 4. Okay, the current potential is 1 minus the previous potential. So it will be 1 minus 3, that will give me minus 2. So it will be 4 minus 2, that will bring about 2. So you can see, right, like accounting method and potential method also, for every operation, we are charging 1 extra. Okay, we are having 2 bits charge. Now the only difference is that we don't have a bank variable in this case. Instead of bank variable, we have this potential function which is taking care of the entire process. And obviously a constant is getting charged. We can't charge something extra, right? If we charge extra in every stage, okay, much higher than this value too, then it would be some light upper bound. We need a tight upper bound. Having light upper bound is like making every single operation expensive. That is not a good case scenario. Okay, it's not a best case scenario. Okay, so let's go for this tight upper bound, and you can clearly see how the values has been worked out. Okay, so I hope you have understood the amortized analysis with the help of binary counter. Okay, now let's understand the comparison. So we can say that in aggregate method, we first analyze the entire sequence, and then we, after getting the complexity for the entire sequence, we calculate the amortized cost by cost per operation. Similarly, in accounting method, we first assign the amortized cost per operation, then check that it shouldn't go below zero, right? So we assign some extra cost to get the amortized cost, and we always see to it that the bank balance doesn't go less than zero, right? We need something extra, extra credits. Now in potential method, it's almost similar, but we just help it with the help of a potential function, right? So it's almost same to the accounting method, but we just don't have any element or any bank variable to store the extra credits. So this is it. I hope you have understood the amortized analysis with the help of all the three methods. That is the aggregate method, the accounting method, and the potential method. And with all the help of three examples, that is the dynamic tables, then we had the stack, and then that is the modified stack, and then we had the binary counter. So I hope you have understood. If you have understood the entire concept, please like, share, and comment on my videos. And thank you so much. Happy learning. Enjoy algorithms. Thank you.